We need to move on now to our second talk, which will be given by Jack Burns. Jack is a professor at the University of Colorado, was one of the original investigators with the NASA Lunar Science Institute, and is an investigator currently with Survey. And he's going to be talking about transformative astrophysics from the far side of the moon. Jack, please go ahead.
Yeah, thank you, Greg. Can you hear me and see my slides?
Yes.
Great.
Yes, on both. Great,
thanks. I'm disappointed this morning that we're not all together in person because, of course, originally we were supposed to be in Boulder, Colorado. But I am looking forward to next year being all together once again in person. That'll be a lot of fun. So today what I'm going to do is talk about the far side of the moon. And the far side is a unique location in the inner solar system that enables transformative science. The far side, of course, is the location of the oldest, deepest impact basin in the inner solar system, the South Pole Aitken Basin. But in addition, it's unique in that it is radio quiet at frequencies below the FM band. It's the only place in the inner solar system that enables transformative astrophysics to be able to observe early epochs of the universe that are not accessible any other way, as well as to also look at issues of habitability of exoplanets. So we've known, going back all the way actually before the Apollo program, at scientific conferences, there was discussions of arrays of radio telescopes on the far side of the moon. But what was lacking up until relatively recently is what I like to call a killer app. That is a scientific application with compelling astrophysics, decadal level astrophysics that uniquely requires low frequency observations from the lunar far side. In recent years, two very strong science cases have emerged. One is that early universe, the dark ages, as I mentioned before, and cosmic dawn that I'll be talking a little bit about. And the other case has to do with exoplanets. And here's a nice tie-in to what Jim was talking about. This is magnetospheres and space environments for exoplanets. So let me start off with one of two missions that I'm going to describe. These are mission concept studies funded by NASA over the last year that describe some of this science. Administrator Bridenstine gave a very nice shout out yesterday to this first mission, Dapper, which is a small set that we plan to place in low lunar orbit. It will operate at radio frequencies in the low band between roughly 17 and 35 megahertz, and also be able to go up to as high a frequency as 100 megahertz. This particular satellite will open up investigations of the early universe. So on the left-hand side, what you see is basically the science case for Dapper. This is a cartoon picture of the evolution of the universe from the Big Bang to today. Is logarithmic in time. Our first picture of the early universe is the CMB, the cosmic microwave background, about 4/10 of a million years after the Big Bang. And this is a time period where the universe has expanded and cooled. So the first atoms formed, electrons and protons came together to form neutral hydrogen. In fact, the baryonic content of the early universe at this time in the intergalactic medium is dominated by neutral hydrogen. But there's no stars. This is why it's called the dark ages. And basically that means there's no astrophysics. So this is the ideal playground for us to really test rigorously the standard models of cosmology and look for deviations. About 500 million years later, the first stars turn on. Models indicate these will be very massive. They will emit Lyman alpha ultraviolet light and begin to ionize the intergalactic medium. That process continues until the entire intergalactic medium is reionized about 1 billion years later. These are nice ideas. They make sense. They're consistent. The problem is there's absolutely no data to test it. Neither the Hubble Space Telescope nor the James Webb Space Telescope can penetrate to these very large distances. But there is one way to be able to probe this epoch in the early universe, and that's again using the neutral hydrogen and the hyperfine transition of neutral hydrogen that comes from the 21 centimeter line. It's because of the redshift, the expanding universe, that wavelength is greatly elongated, that we actually observe, and the frequency is compressed to below 100 megahertz or so. But it is available. So that's what I'm going to be talking about. Obviously, this early universe has generated a lot of attention in the scientific community. 3 Nobel Prizes in cosmology in just the last 15 years. So a lot of core basic physics to be found here. So Dapper, the basic mission, as I alluded to a moment ago, is such that the satellite's going to be placed in the radio quiet cone. That is, when it is in that cone as part of its orbit, it will be taking data on the early universe. The antennas are very simple cross dipole antennas. We have almost no spatial resolution, but we do have good spectral resolution. So the deliverable from this mission will be a spectrum. Think of this as power in the radio receiver versus frequency. And what we're looking at are component spectral signatures for the early universe. The spacecraft is a very small one, 8/10 of a meter in the longest dimension. It's spinning, and we deploy these long dipoles for the low band part of the experiment, and it has this large peanut-shaped antenna beam. Once again, the deliverable is the spectrum. Here you see the results from a detailed end-to-end simulation that we've done that includes all of the various noise components, statistical plus systematic uncertainties associated with the sky, the foreground, and the instrument. And as you can see in the spectrum, there are 2 large troughs, one associated with the dark ages at low frequencies. And as I mentioned, this is a playground for cosmology. So the standard cosmology model makes a very specific prediction of the characteristics of this trough. Any deviation from that is going to indicate new physics and exotic physics, possibly physics related to non-gravitational interaction between dark matter and baryons. And then the cosmic dawn trough is going to tell us when the first stars turned on and what their characteristics are. I'm going through a lot of this very rapidly. Let me point out a number of talks and posters by members of my team and colleagues that are listed here over the next day or two. All right, let me move on to the second mission concept that we did this last year called Farside. And in this case, it's actually an acronym, as you see here. This is an array on the far side of the moon. Here are members of the team. Greg Hallinan from Caltech and myself are the leads. JPL and their Team X did an absolutely sensational job of working on the first engineering design study of this array. So we feel like we have a good handle now on these characteristics. Here's the science. And again, this relates somewhat to what Jim was talking about a few minutes ago. This is exoplanets and habitability of exoplanets. I'm going to start off with an analogy of Mars. We know that 2 billion years or so ago, Mars was wet and warm, but when its magnetic field shut down, then its atmosphere started to be stripped by the solar wind. We see that today with MAVEN as that stripping continues. And the net result is it transformed Mars into the desert planet that it is today, and no obvious signs of life, at least on the surface of that planet. So the space weather from the host star, along with the magnetic field, are 2 added ingredients associated with habitability that we need to explore. So being just in the habitable zone is not enough to know if a planet could be habitable. The kind of stars we're going to be looking at nearby are Endor Stars. So that just is because the majority of solar neighborhood stars are in this category. These are lower mass, lower temperatures, which means the habitability zone is within about 2/10 of an astronomical unit. so pretty close to the star. One of the problems with these Endor stars is they're very bursty. They emit a lot of X-ray emission, some radio emission. In analogy to the sun emits coronal mass ejections, and associated with them are type 2 and type 3 solar bursts in the radio, generally below 10 megahertz. These are associated with shock regions, which expand out into the interplanetary medium, but they allow us to probe the space weather. In addition, these shocks also energize particles in the magnetic fields and raise the auroral emission by orders of magnitude, making them potentially visible also in exoplanets. This gives us a handle at low frequencies to being able to probe the space weather. The magnetospheres themselves, the frequency of radio emission is directly proportional to the magnetic field. Here you're looking at flux density versus frequency for planets in our solar system. Only Jupiter is visible from the ground because its magnetic field is so high. Everything else, including the Earth, is below the ionosphere cutoff on the Earth. So that means we have to go to space, we have to go to the moon to observe these planets. And similarly, Earth-like habitable planets around other stars, we would need to go to the moon. So here's the Farside mission concept. We're going to operate all the way down to 100 kilohertz. That's 2 orders of magnitude below the ionosphere cutoff of the Earth. We'll use a commercial lander. We've been working with the Blue Origin company and their Blue Moon lander to baseline this. 1 or more rovers, which will then deploy these tethers, these science tethers that will be used for power and communication. And we'll put out 128 of these nodes. They will be distributed over an area of about 10 kilometers or so in this petal-like configuration. The node itself, the individual antenna node, some of that is derived from the Sunrise heliophysics mission. In our case, we have these tethers, which will also have the low frequency antennas embedded. These will be 100-meter tip-to-tip thin wire antennas, as well as stacer antennas for the higher frequency. To operate during the day and night, we'll have a radioactive heater unit to survive the night and radiators to be able to operate during the heat of the day. So when you put all this together and look then based upon an end-to-end study, this is kind of the deliverable. This is what we think we'll be able to see. This is the flux density from exoplanets versus distance. And here we're looking at the magnetospheric emission. The colors represent different models of enhancement due to the stellar wind. But we have several dozen exoplanets are in view here to be able to determine and measure their magnetic field, and then add that to our understanding of potential habitability. Here is a video that we put together just showing a little bit of the mission concept, the deployment of the rover off of the lander. The lander will also have our correlator, our power station with 2 MMRTGs, data and command. Here's the rover deploying a polyamide tether and one of the antenna nodes here with the stacer antennas coming out from there. So let me just, thanks, Greg. Let me just show one last thing here, and that is we've been also working on a prototype of a small mission to get us started, a 6-element interferometer in an L-shaped configuration here that is capable of doing some imaging of type 2 solar bursts. What we want to do is use the sun as well as Jupiter and possibly Saturn in our solar system as prototypes of what we would be doing with Farside for exoplanets. But importantly, buy down risks. We'll use the JPL Axel rover to deploy the tethers and buy down risks on mobility, deployment, operations, and also understanding the interactions with the lunar surface. So let me just put up the last slide here and conclude that the Artemis program, the CLIPS program, it is beginning to open up for the first time access to the moon and to the far side of the moon for doing low frequency radio astronomy. Dapper, Farside, and Prime are missions that we are eager to pursue. So with that, Greg, I think I'll just stop there.
Excellent. Thank you so much, Jack. And it's great to see the progress that you've made since we first met back in the NLSI days. Just fantastic. And please feel free to put your questions in chat. I'm not immediately seeing any, and so maybe I'll ask one, and that's what's the angular resolution that you're expecting from Farside, and given previous cosmological results, would you expect to see any structure at that kind of angular resolution?
So Farside, again, the principal design there is for exoplanets, although we are going to be pursuing some cosmology. Right. And the angular resolution will be roughly 1 degree or so. That's good enough to be able to monitor where radio emission is going to be. So with this array, we're actually going to be sampling the entire sky in 1 minute intervals with this angular resolution, 1400 channels, so that we can monitor thousands of exoplanetary systems and look for bursts that would be associated with space weather, with coronal mass ejections, and enhancements of the magnetic fields. So this is really an all-sky monitoring telescope that has sufficient resolution to deal with the nearby exoplanets.
Great, thank you. And there is one question in chat from our friend Mark Kleinvolt in the Netherlands, and he says, Jack, are you also considering techniques like additive manufacturing to build antennas on the moon?
Yes, in fact, we're working with a group in Houston, Lunar Resources, on a mission concept to manufacture antennas on the surface of the moon. We're actually hoping to submit that as part of the PRISM program.
Excellent. Excellent. Fantastic. Well, thanks for a great talk, and good luck with all this.
Thanks. Thanks very much, Greg.